Yeah. Okay, I think everything is set. Meeting is recorded. Got it.
I think we have just to wait. Can you hear me?
Yes.
Okay, just wait for a couple of minutes because it's not 2 yet. It's 1:58.
Swiss. Well, not really. Not.
We still have people joining, especially online.
I have a blackboard in my office, and yeah, yes. So it's a long story, but the short version is that I inherited the office from somebody who retired, and I thought because it's so cool. But then when you have a blackboard in your office and they clean it every 2 weeks, you realize that it's not so cool. So I stopped using it. And then I thought, okay, if I do something which is, like long term, that I only update every year, then I don't create tons of chalk powder and it's cool. And then background slide.
Nice, looks cool.
Mm-hmm.
Okay, now it's 2. I think we can start. Let me just make a quick introduction. Can everybody there listen to me well?
Yeah.
Okay. So it's my my pleasure to introduce Michele Ceriotti, who is our next speaker. That in fact he doesn't need any introduction. Everybody there in the public knows him well. Michele is a professor at the Institute of Materials at the EPFL in Lausanne, and his research focuses on methods for molecular dynamics and quantum simulations, development of machine learning techniques for atomistic systems, application of those models for problems in chemistry and material science. And I'm really looking forward to your talk, Michele. So the floor is yours.
Thank you, Mario. Thanks, everybody, for joining in person or remote. It was really nice to get invited to this meeting because and machine learning is basically what I ended up the past few years, but also what I have been doing since the end of my PhD on the quantum dynamics side. So the presentation is going to be a little bit of a, how can I put it, kind of a big mix, because I'm trying to touch upon both sides. I had initially prepared a short talk, so then I realized that I had an hour, so I extended it. But this is to say, please, both in person, stop me if there is anything more informal. So, how typically I used to motivate to myself and to others what I was caring about quantum dynamics and quantum fluctuations. As I keep telling to my students, one of the reasons for doing molecular simulations is that you can look at the atoms and see what they are doing. And if you just take a chunk of ice and you look at it in terms of pretty much the simplest approach if you want to compute the stability by some kind of first principle method. Oops, wrong button. Or you look at a simulation of, let's say, 100 Kelvin, you start seeing that the atoms are jiggling around quite a bit. But if you perform a simulation that also incorporates the quantum mechanical nature of the nuclei, fluctuations becomes really large. Amount of distortion that molecules in crystal undergo of the atoms is really, really substantial. So the problem, and I don't know how many are familiar with Path integrals, because it would have been a bit of a homogeneous mix of people from quantum dynamics, people from machine learning. So I also a little bit of more sort of introductory stuff. So why is not everybody operating quantum nuclei? That's a legitimate question. I try to convince you that quantum effects on the nuclei are important. Why isn't everybody doing that? So at least part of the reason is that incorporating quantum effects is quite complicated. So, basically, you know, the one idea would be that you would also solve the Schrödinger equation for the nuclei the same way you solve the Schrödinger equation for the electrons. Somebody does this, it's very complicated, and most of the time it's not really necessary. What you can do instead is use a very elegant formalism that maps the quantum mechanical statistical problem onto that of a classical ring polymer. So the idea, you know, usually when you see a cartoon introduction to ring polymer and path integral methods in general, you see plots like these, like, you know, several balls held together by springs. And I actually think that this is a very misleading view of what goes on into a path integral calculation. Because what goes on in a path integral calculation that you can see very clearly if you look at the form of classical Hamiltonian that you sample in order to do path integral calculations is basically made up by a sum of classical Hamiltonians. So effectively, at this level, the path integral Hamiltonian is like multiple parallel universes. You have multiple copies of your physical system, each governed by its own potential. So the atoms, you know, Born-Oppenheimer, machine learning, semi-empirical potential, and a perfectly classical kinetic energy. And then there is an additional term that appears when you actually consider the quantum mechanical kinetic energy contribution of the path integral, which corresponds to springs that the same index. This is all done for indistinguishable particles, for distinguishable particles. If you want to incorporate fermionic or boson exchange, it's a different story that I'm not going to touch upon. But basically, you add these springs that connect the atoms. That's it. And then basically you sample these classical Hamiltonian and you can observe both the corresponding over the position of the nuclei. Furthermore, you can also, caveats, I will not get into this unless you really want, you can get recent estimates of the dynamical properties of systems that are not too extremely quantized, essentially systems in which the quantum mechanical part of the dynamics is not due to coherence, but is due essentially to a change of the energy surface the atoms move on. So you can, essentially by running molecular dynamics on this Hamiltonian and taking the dynamics seriously, even though in principle you should not, but if you do that, you get pretty decent approximations to the quantum mechanics of the nuclei. So the problem here is that in order to converge all of these observables, large number of parallel universes. This has to be larger than h bar omega, where omega is the frequency of system divided by k. Basically means aqueous systems at room temperature 30 to 60. So this is way, and for each of the parallel universes, you have to run a separate calculation of the potential. So this is very, very expensive. So to play, I mean, to be honest, I spent like 5 years of my life developing methods to cut on the cost of path integrals so that you could run ab initio path integral molecular dynamics. But if you ask me now, I think that, you know, you can still use those, you should use those, but really one easier way of getting away is making it expensive. And this is pretty much exactly what machine learning does. Rather than computing the potential for your system by solving the Schrödinger equation, you use a surrogate model make the same prediction at a lower cost. And I'm sure that you have seen at least 10 of these of slides very similar to this one over the last 2 weeks. So something I want to know is that, of course, there is more to life than energy and forces. You might want to compute polarizabilities, dipole moments, charge density, whatever. And I will spend a bit of time during my presentation to talk about how you can build not only machine learning potentials, but more broadly machine learning. So to start, let me start with something which is a little bit formal, but apologies and try to hold with me. Over the past few years, machine learning is growing at an incredible rate. I mean, I'm an editor for GCP, and every 2 days, not using machine learning, but using some new machine learning technique. So it's an unstoppable flood. And so I thought that, that'd be nice to try and take one step back, try to look at machine learning models from a more detached and formal perspective. So do we really need one new machine learning model every 2 days, just on GCP? So from a purely mathematical perspective, if you look from, at the end of the day, the whole idea behind the machine learning model is that it should be some kind of abstract approximation machine to which you feed data and you get an answer. So the question is, what is the data that you're feeding to this machine? The data, if you are trying to approximate the solution to a quantum mechanical problem, are, I keep pushing the wrong button, are the positions and the nature of the atoms. So from a mathematical perspective, the inputs of our models are basically point cloud. It tells me whether I have carbon, hydrogen, or oxygen. Another perspective, which is kind of alternative to this, and which is very much used in traditional cheminformatics approaches, is to regard a molecule as a graph. So basically, each atom is a node in a graph, and the relationship between the neighboring atoms form the edges of this graph. The mathematical theory is called geometric deep learning is very, very well developed. There is a super nice review here that really covers a lot of the traditional development in the field. But how about what goes specifically in an atomistic model? What goes specifically when we are not describing an arbitrary point cloud, but are describing a molecule or a material? So the idea is that what we are trying to do is a mathematical mapping between a structure going through a representation. These might be more or less explicit, but we usually go through some kind of mathematical representation, and we want to map these to a property, our potential, dipole moment. So the physical nature of this mapping has consequences for the type of priors, so for the type of assumptions that we make on the structure of the model. So for example, the vast majority of cases, if I move the atoms smoothly in dimensional space, associated with the structure will also change smoothly. This is why then we can compute derivatives and get the forces. So to have a machine learning model that is smooth, just as the properties that is trying to predict. This is not only to be able to compute derivatives, but also to. This is dead? Yeah. Okay. Shall I go on? Or, Does it work? Okay. So this is not just to be able to compute derivatives, but also because the smoothness implies easier interpolation. It basically means that you need less data. If you can't make a smoothness assumption, you might need a large amount of data to achieve an accurate interpolation, because this is essentially what we're doing, interpolating. So second requirement, which seems trivial, but it's not. And unless you ask, I'm not going to get into much detail, but we have been having a lot of fun trying to solve very subtle problems related to this issue. So you want your mapping to be complete. Here, complete is not the correct mathematical term. We should say injective, but completeness gives the idea of the fact that you want basically to be able, anytime two structures differ, to be able to predict that they have different properties. This may seem trivial, but is made less trivial by the simultaneous requirement that the mapping be symmetric. So we want at the same time, and again, this is both something that helps from the point of view of data efficiency and something that helps in that you make sure that some fundamental physical requirements are exactly enforced. You want your mapping to be symmetric in the sense that if you apply some trivial symmetry, such as a permutation of the labels of atoms, rigid rotations or rigid translations, you want that the property doesn't change. Or if the property is, for instance, a vector, you want the property to transform covariantly with the rotation. So actually, the simultaneous requirement of symmetry and completeness is not so easy to enforce. But if you want to know more, these are a couple of papers that discuss the weird issues that can occur here. So one final requirement, which is not really a requirement, but is something which is so useful that is now become almost universally used, is the notion of building models that are additive. With additivity, what I mean is that you write the property of an entire structure, I'm calling the structure A, as a sum of atom-centered contributions. So this basically means that you can build up models that, even though they are interpolative, strictly speaking, because they interpolate only among local environments, they become extrapolative because you can put many local environments together to form a structure that has nothing to do on a global scale with anything that you have in your training set. Okay, so this is basically how you can get models that on a global scale are clearly extrapolative, but actually, since there is no magic in machine learning, they are really interpolating because they interpolate locally and predict extrapolating globally. So this means that most of the time, and for most of what I will talk about today, the focus of what we are trying to describe is not an entire structure, but an atom-centered environment. So basically, a collection of interatomic distance vectors. So you see immediately how shifting the focus on atom-centered environments immediately makes the model translationally invariant, because it only depends on distance vectors rather than on the absolute position of the atoms. So it's somehow harder to build a model that is performing and sort of behaving correctly with respect to rotations. So if you have a model that is equivariant with respect to rotations, what you want, and I will return to this, but what you want is that if you rotate your structure, which basically means rotating in the same way each of the interatomic distance vector, then the prediction should be exactly equal to a rotation operator applied to the target property. So if the target property is a scalar, it shouldn't change. If it's a vector, it should rotate. If it's a YLM with L equal 4, it should transform like a Wigner matrix with L equal 4. So you see basically how a physical requirement, so symmetry, equivariance, translates into a requirement on the model. And another symmetry requirement is basically that the model be invariant with respect to the ordering of the atomic labels. This is basically means if I list the hydrogens as 1, 2, 3, 4 or 1, 4, 3, 2, the answer should be exactly the same. So it turns out that when you ask so much in terms of mathematical constraints that should be fulfilled by your model, you restrict a lot the design space of a machine learning model. And one of the most, to me, interesting findings that we made over the past 3 or 4 years has been realizing that actually these dozens of alternative machine learning frameworks all do pretty much the same thing. And what essentially they all do is take atom-centered, basically atom-centered neighbor densities. So basically I sit on an atom and I build a function that describes the probability that I have a neighbor in a certain position. Then you build tensor products of these, and you use these discretized on an appropriate basis as the vector of features that describe your structure. You have many different choices for a basis. You have many different choices for how you compute this expansion. And therefore, there is space for 150 different models. But each of them is essentially computing an alternative form of these symmetrized correlation functions. So these actually looking at these density correlations immediately makes the model invariant to the atom labeling, because the density doesn't know in which order you are adding the atoms to it. And then in order to make the description invariant to rotations, you need to average over the rotations this tensor product. Now, I'm not going to get into the technical details, but basically this idea that what you do is building a symmetrized correlation of the density means that the only reasonable way of building these objects is by stacking Clebsch-Gordon. Basically, each density expansion, if you write it on a basis of spherical harmonics, transforms like an angular momentum. And when you build the symmetrized correlations, essentially the only way you have to do it is to combine YLM using Clebsch-Gordon coefficients. And so basically, we modified this density correlation framework to get an equivariant framework, and it's all angular momentum algebra. That's pretty much all that there is to it. And actually also, if you look at the, in the machine learning world, there is a lot of excitement about equivariant machine learning models. All that they do is stacking with a, machine learning language. They stack layers that are Clebsch-Gordon products. That's the only thing that you can do if you want to start from 2 irreducible representations of SO3 and getting out an irreducible representation of SO3. So this we have also extended, and actually this is something that has been done by Andrea Grisafio, who is in the audience. We extended these to also incorporate a way to describe long-range physics, which is clearly absent from a framework that relies only on short-range cutoffs of the neighbor density. And very recently, we have also shown that if you center some of the atom densities on the neighbors rather than on the central atom, you get a systematic construction that is equivalent to message passing neural networks. So basically, in the appropriate limit, message passing neural networks can be replicated by a systematic expansion that centers atom densities on different tables. So, okay, so this was kind of, I mean, it's something that I included because I'm very much obsessed with it. But I think that at the end of the day, what is really nice is that once you have put together all these mathematical frameworks and implement it, you have a very powerful tool that allows you to make predictions for the properties that you would need to run DFT or better to obtain. And instead, you can get them really for cheap. And so something that we started doing was looking at the thermodynamics of materials, because after all, I'm in a material science department, using machine learning models sort of as a stepping stone to get ab initio quality thermodynamics. And we started with water because water, quantum effects are important with water, and quantum effects are very close to my heart. But what is interesting here, and something which I suspect, it will take several years before it can be completely overcome. If you really want to get the level of accuracy that you need to say something, for instance, on the relative stability of different phases of water, I will give you an example here where the difference is of the order of 0.5 MeV per atom. It's going to be very hard to get machine learning models that are accurate enough. So what we did here is something very pragmatic, because every now and then you have to be pragmatic. And basically, we do all of the time-consuming thermodynamic integration, path integral sampling that you need to get thermodynamics of water phases with quantum effects included. We did all of these at the machine learning potential level. And then we did a few single point ab initio calculations to do free energy perturbation and promote the free energies that we had got at the neural network level to full ab initio level. So basically, essentially, we can get the same accuracy relative to ab initio than one would have needed, a million force evaluations to compute. We can get it with a couple of hundred single point calculations. And here we we used RefPB 0, which is a functional that, for good or for bad reasons, is very good for water close to room temperature. So there is always, when you do DFT, there is always a little bit of a hyperparameter optimization in the choice of the functional among the 100,000 that you have to choose. But at the end of the day, with the only cheating involved with the choice of a suitable functional, we could basically get melting point of water to within less than 5 Kelvin. And this is not for cancellation of error. This is for the good reasons. We get the difference in melting point between H2O and H2O. We get all the effects that should be there because also the quantum mechanical nature of the nuclei, including the fact that hexagonal ice is more stable than the cubic ice, which is something which is known to be related to very, very small difference in free energy, because you can observe stacking defects in ice, and because you can find the cubic ice in an astrochemical setting. So it's very well known that the difference in free energy must be really tiny. And after we put all the pieces together, we can get it. Another example, and I really like this a lot, because, so this is the melting curve, the heat capacity curve of nickel. And this curve has so much physics in it. So at low temperature, you have the deviation of the heat capacity from the classical limit, undergraduate solid state physics, one of the most blatant examples of how quantum effects affect matter, not only at cryogenic temperature, but, well, okay, nickel is heavy, but, if you do this for diamond up to 500, 700 Kelvin, you are still very, very far from the classical limit. But what you can see at high temperature, so basically here we have to do path integral calculation, but high temperature, even though we have a potential which is trained on DFT, and we know that DFT is pretty good for nickel, there is still a 25% difference between the heat capacity from the potential and the heat capacity of actual nickel. And the reason actually is related to electronic excitations. When you heat a metal at 1500 Kelvin, electrons also get excited. So there is an electronic contribution to heat capacity. And what is nice here is that we don't get it by running additional DFT calculations, but we have a machine learning model for the electron density of states, and we use it to predict the electronic contribution to the heat capacity. And this other bit is basically the ferromagnetic transition in nickel. And we have nothing this far to incorporate it, but there are others who are working to include magnetic effect in a machine learning context. So more generally speaking, I mean, I think that this example in which we predict the density of states to get the electronic heat capacity is a good example of why it's useful to predict not only a machine learning and thermal potential, but also machine learning models of other properties. Now, one of the issues that you face if you want to do that is that a lot of the properties that you would like to compute are not as simple as the potential. They are not just scalars. So as I had anticipated, if you want to learn something that is a vector, dipole moment, for example, you want your model to be equivariant. So basically, this means that if D has 3 Cartesian coordinates, X, Y, and Z, and I rotate my molecule, the spoiler alert, basically, I want the dipole moment to rotate like a rotation matrix. So from the point of view of the machine learning model, what this means is that your machine learning model must be built with symmetry awareness, incorporating indices that allow you to span the irreducible representations of the rotation group. So here for the dipole, which is basically like an L equal 1 term, it's easy, it's just a vector. You can see these. So this is a fancy notation that we're using. Not everybody likes it, but basically the idea is that here I'm trying to describe an environment centered on atom I, and I have a number of features. So these are basically descriptors of the molecule. But if I want to make a tensorial prediction, the descriptors must have an additional index that is associated with the symmetry. And it's important to keep the two indices separate, which is why I use this bracket notation, because in the bra, I'm putting the index that enumerates the features, because I don't care. This is just a projection of an abstract object on a basis. But this index is important, because this index describes X, Y, and Z. So this is what I need to have the appropriate rotational behavior of my prediction. So for a linear model, this is just a fancy way of writing a linear model. I have some weights, one for each feature, and I will optimize these weights. But if I can build a machine learning model based on features that themselves transform like vectors, then I'm done. I don't need to learn anything to get the correct rotational behavior of the vector. So this is basically in 3 minutes what equivariant machine learning is all about. Building models that have the appropriate algebraic structure so that you can get automatically your vectors to rotate like a vector. So you can use this literally to learn the dipole moments. And this is something that we did in this paper. But you can also use this to learn any property that has a tensorial nature by first converting it into reducible spherical components. Here, I don't know how much. So you take the polarizability, the trace is a scalar. It's a symmetric tensor. This means that on top of a scalar contribution, there is another contribution which is associated with the off-diagonal term and the traceless part of the diagonal that transform like an L equal 2 spherical harmonic. So all of this stuff, thanks to Wigner back in the books from the 20s, basically you can find all the expressions, and then what you need is a model in which the features transform like spherical harmonics. So if you rotate your structure, the rotation of the features must be described by a Wigner D matrix. And you can realize the features with this behavior by decorating your density correlations with a set of spherical harmonics. So that's the essential idea of what you're doing. And with this, you can build models of properties that are tensors. So you can build models, for instance, for the polarizability. And so there are 2 things that are kind of nice on this slide. First, you can get models that are pretty accurate. And also thanks to the fact that the DFT is not very accurate for response properties, we can get a model that is trained on couple cluster polarizabilities for small molecules. And I mean, when I mean small molecule, I mean fewer than 7 heavy atoms. And we can make predictions that are in a way extrapolative by making predictions of models or molecules that have up to, I think the largest we could run had 14 heavy atoms. And even when making predictions out of sample, essentially, the model is more accurate with respect to couple clusters than DFT is. which I think is kind of nice. And the reason why we can do these extrapolative predictions is that the model is atom-centered, meaning that the total polarizability is built as a sum of atomic contributions. And this atomic decomposition is very important because here I'm basically plotting the atomic contributions. You can see, and this should come as no surprise, that if you have a conjugate system, the polarizability in the plane of the molecule is much larger than the polarizability in the opposite plane. Now, let's say that I was trying to predict the polarizability, the macroscopic polarizability of a molecular crystal. Now, when I combine the different molecules, they might be oriented in a different way, and so I need to be able to sum in a tensorial way the contribution from individual atoms, otherwise it would never work. I would never be able to predict how the relative orientation of the molecules in the crystal affect the macroscopic polarizability of the crystal. So you can do even more complicated stuff. Again, I hate to keep bringing up Andrea, but this is another work that wouldn't have happened without him. And basically, you can also use these to learn the electron charge density. And the reason why I say that this wouldn't have happened without all of this tensorial stuff is that we do this by first expanding the density on an atom-centered basis, basically like in a resolution of identity framework, and then we machine learn these expansion coefficients. And then you need all of these equivariant machinery, but then you can train, again, you train on small molecules and you predict on crystals. You train on small molecules and you predict on proteins. And this is because of this additive structure of the model. Final example of a property, and this is very recent, you can make predictions for the matrix elements of an effective single particle Hamiltonian. So this would be pretty much equivalent to a tight binding Hamiltonian, but we can learn the matrix elements from a self-consistent Hartree-Fock or DFT calculation. So basically we get an algebraic form which is the same as a tight binding Hamiltonian, but we can train it on DFT or Hartree-Fock calculations. And the reason why I'm showing this is kind of a cute example. So we build in only fundamental symmetry, rotational invariance, permutation invariance. However, all the point group symmetries are subgroups of the combination of rotations and permutations, which means that if you make predictions for a molecule that is symmetric, benzene, which is D6H, the model is bound to make a symmetric prediction, a prediction that is consistent with the 6H symmetry. So here what we're doing is really a little bit crazy. We train on a single molecule and we basically take a 30 by 30 matrix, which is basically minimal basis representation of the electronic structure of benzene, and we fill it with random numbers. We only make sure that it's symmetric, nothing else. NumPy random uniform. When we fit and then predict, we just cannot predict this matrix because a random matrix is not consistent with the 6H symmetry. We only predict the symmetric part, which means that, for instance, the molecular orbitals, the energies are completely random, but the symmetry of the orbitals and the degeneracies are consistent with the character table of the 6H. Okay, so basically, symmetry is as if your model, as I'm writing here, knew molecular orbital theory, which is something which is, I think, pretty nice. So when you put these models of properties together with the models of potentials and thermodynamic stability, you can start do the kind of stuff that people have been doing with heroic efforts with ab initio molecular dynamics. Now you can run them on your group cluster rather than on a national level HPC platform. And here we are revisiting the stability of barium titanate, prototypical ferroelectric. And we build not only a model of the potential, but also of the polarization, which means that we can predict all of the phase transitions that this material undergoes, but also compute the dielectric response entirely from a machine learning framework, which is, I think, very easy. Now, I want to give another example of an application, this time bringing in quantum nuclei. This is a collaboration that has been going on for a few years with the group of Lyndon Emsley at PFL. He's an experimentalist. He is an expert in NMR crystallography, among other applications of NMR. And the idea in NMR crystallography is that you compute the chemical shieldings of a crystal of a known structure, and then you determine the structure by comparison with a set of candidates obtained by crystal structure prediction. So there is always a very strong interplay between modeling and experiment to do this. And one of the rate limiting steps is the calculation of NMR chemical shieldings by GPO-DFT, which is much more expensive than an energy and force calculation. So what we did together with Lyndon's group was to build a model, ShiftML, that allows you to predict chemical shieldings of atoms with pretty much DFT accuracy, so that you can identify the different, among the different polymorphs, what is the one that is actually being observed. And since now we have a way of potentials, but also predicting the chemical shieldings, we can start looking at some of the assumptions that are usually made when one does predictions of chemical shieldings in simulations. So for instance, most of the time, these predictions are made on local minima of the potential. But that's not what an NMR experiment measures. An NMR experiment measures the average over the fluctuations. And if you run a path integral calculation for a molecular crystal, and you look at the distribution of chemical shieldings, the spread is huge. Then, of course, the only thing that the experiment sees, well, not really, that's the only thing that the experiment sees that I understand well enough to explain, because NMR is very complicated. You can measure a lot of things, but that's well above my pay grade. But the simplest thing that you can get out of an NMR experiment is the chemical shielding, which is essentially the average of these distributions. So certainly the average is shifted less than this huge spread, but still I mean, yeah, we did this for 3 different crystals, but what I wanted to show you is that also the change in the average can be significant. And so here the figure is a little bit of a mess. I should have simplified it. So basically the line that we set to 0 is basically what you would get from a single point calculation of the ground state structure. Then there are different approximations because we wanted to try as much as we could. But what I want you to focus on is the star, which is the experimental shielding, and the red point that is the result of a PIMD calculation. And what you can see is that for every case for which we had experimental data we could use, there is a significant, not always huge, but significant change in the value of the shielding when you consider quantum fluctuations. And every single case, it brings the result of the simulation closer to the experimental one. So essentially, the message would be that fluctuations, and in particular quantum fluctuations, are really important if you want to get the quantitative accuracy in predicting NMR experiments. And you can see this also, we're really scavenging the literature for experiments for those 3 crystals, and we found these measurements of the temperature dependence of the shieldings, which of course the temperature dependence of the shieldings should be 0 if you only consider the mu in the potential energy, but there is a non-zero slope, and if you use path integral molecular dynamics, you get basically spot on the temperature dependence of the experiments. So the last part of my talk, I want to finally get to the Dyn part of the name of this meeting, and on dynamics. So I already told you at the beginning about path integrals and how expensive they are. Now I need to briefly guide you through something that has kept me busy for my PhD and the best part of my postdoc years, which is the construction of generalized algebra equations. I will go very quickly, but just give you the general idea. So the general idea is that, okay, this is Hamilton's equations for a single particle in 1D, okay? So if you want to simulate a system at constant temperature, this is not a good idea because this conserves the energy, no way to describe a heat bath. So one way that is both physically meaningful and easy to implement is to add a noisy force and a friction term that basically translate your Hamilton equations into Langevin dynamics. So characteristic of a Langevin equation is that the noise is not correlated in time. So basically, every time your particle gets a kick, it's completely random. So one way to extend a Langevin equation to make it richer, and actually, if you have ever read Zwanzig, non-equilibrium statistical mechanics or this kind of literature, if you try to derive from first principles the coupling between a system and a bath, you don't end up with a Markovian, memoryless Langevin equation. You end up with a Langevin equation that has memory. This is a generalized Langevin equation, and the structure is the same. There is noise, there is friction, but the noise is now correlated in time, and the friction is not instantaneous. It depends on the past history of the momentum. So implementing these in a simulation would be really painful because you would have to keep track of the past history of your momentum. But it turns out that you can, and it's actually funny because this is essentially the opposite of the derivation that you find on Zwanzig to go from system plus bath to a system with a generalized Langevin equation kind of treatment. You can basically backmap this non-Markovian Langevin equation onto another equation that basically has, again, structure of Langevin dynamics, noise, friction, and the Hamiltonian part, but it's in an extended phase space. So you have a bunch of additional degrees of freedom, and everything is coupled linearly in a matrix form. So what is nice of this formulation is that it's easy to implement, and you can find a lot of stuff analytically, particularly for a harmonic oscillator, because in a harmonic oscillator, also this term, also the force becomes linear. So for a harmonic oscillator, you can solve everything analytically, which means that you can play a lot of really fun tricks, because you can predict a priori what would be the behavior of a dynamics for a given set of values in this matrix when you apply it to a harmonic oscillator with a given frequency. So what you can do is say, well, I'm simulating water, so I will have a vibration frequency from 4,000 inverse centimeters down to very low frequency. And then you can ask, I want a thermostat that is very efficient at thermalizing water across the whole range of temperature. So it's never overdamped, never underdamped, always as close as possible to being optimally damped. And then essentially you can optimize numerically the entries in this coupling matrix until you get something that does exactly what you want. And one of the things that you can do is actually to break the fluctuation dissipation theorem, at least the classical fluctuation dissipation theorem, and get a generalized Langevin dynamics that does something more than being efficient at sampling. It also gives a different temperature to normal modes depending on their frequency. And this is really cool because if you look at the phase space distribution of positions for a harmonic oscillator, it's a Gaussian, just like a classical oscillator. However, the dependency of the width of the Gaussian on temperature is more complicated. It depends both on temperature and on the frequency of the normal mode. And you can basically realize this with a suitably tuned generalized Langevin equation. We call this a quantum thermostat. And what is really remarkable is that this works pretty well also for strongly anharmonic systems. So you basically run this machinery on a quarter double well, and you get pretty decent agreement as a function of the height of the barrier for the different properties that you would compute from an average. Now, in reality, when you want to do this and be really accurate, this using color and noise alone is not enough. So the idea that we had was to combine path integrals with this color and noise machinery. And the idea is that if we could devise some intermediate forms of color and noise, we could converge systematically, but faster. And here you can see this is a little bit cheesy, sorry, but this basically the idea is that you converge, in this case, the quantum kinetic energy. Using color and noise, the convergence is much, much faster. So you get fully converged quantum estimators with 6 replicas rather than 32. That's the basic idea. Now, the problem is that when you do this, you really devastate the dynamics of your system. So this is a little bit extreme, but I'm taking, this is on a log scale. So it looks weird is because it's on a log scale. This is the vibrational spectrum of liquid water. You can reconstruct stretches, bands, and the vibrational peaks. And so here we designed the generalization equation to really destroy this spectrum, okay? And it does. So if you run this GLE and you measure the velocity correlation spectrum, this is what you get. It doesn't look at all like the spectrum of liquid water. This is the problem in general of thermostating. The dynamics is disturbed. So the point is that, again, in the harmonic oscillator limit, you can predict exactly how the GLE will affect a harmonic oscillator of frequency omega. And this looks like a little bit as a convolution kernel. So knowing only the form of the GLE and knowing the distribution of normal modes for NV dynamics, I can predict how the dynamics will look like in the presence of the GLE. And the prediction is really good. So this red curve is what I get taking these that I know a priori from the form of the GLE and these that I know from the NV dynamics. So I can predict almost perfectly how the dynamics will be disturbed. This suggests that we might also be possible to do the opposite operation. So a deconvolution that starts from the dynamics that is disturbed by the GLE and recover the dynamics without a disturbance. And this works incredibly well. I mean, this was really done to destroy the dynamics completely. And after we run this deconvolution procedure, we have the stretches, the bands, everything is in its right place. Now, if we consider a case which is less, catastrophic, so this is a pretty aggressive white noise management thermostat, we recover almost perfectly the microcanonical spectrum, even if we run a GLE dynamics. And so something that we did a couple of years ago was to extend these also to the case of this path integral plus GLE. So again, I'm probably putting too much meat on the fire here, but so here the idea was that we, if you do a simulation with this color noise to accelerate the convergence of path integrals, and then you look at the velocity correlation spectrum, you get this broad thing where you can barely recognize anything. But if you run this deconvolution procedure, you get your peaks back to look reasonably close to QCMD, which is arguably the best thing that you can do for condensed phase quantum dynamics. There is still a little bit of broadening, but this is up to a factor of 10 cheaper, so it's something that might be interesting to do. And I want to show you also that in the same paper, I mean, we run all the...
Michele, just to let you know, have 5 minutes.
Yes, I'm finished. So basically, just to show you that you can also do these, in here we're using polarizations and polarizabilities from a machine learning model. And you get, so basically you can compute IR Raman spectra of liquid water, and it's so cheap that you can also afford to do 2 different hybrid DFT functionals and check how much they change the spectrum in the presence of also quantum nuclear effects. And yeah, something I really like to close this part on this figure, because this is This was actually done by 2 former students. And one of the nice things of having good students is that when they leave, they don't stop being good. And so they also extended these, and now they can do some frequency spectroscopy for surface of water and time domain, a lot of nice stuff using these integrated models that compute both the potential and experimental observables. So what next? So I think that one thing that I really want to keep working on is this looking into the nature of machine learning models, because all too often you get machine learning models as a little bit as a pre-mixed object, with a brand, and you use it, and it has a lot of choices that have been made for you. So what we are trying to do instead is understanding what are the different ingredients that go into a machine learning model, so that basically somebody who wants to use machine learning for an application can do their own mix and choose the combination of ingredients that is most fitting for a given application. And something else that we're trying to do, which builds a lot on these equivariant models that I told you about, is to build models that are neither physics-based nor data-driven. So the idea is that essentially you would use machine learning to predict some of the ingredients, but then use cheap to compute physics-based expressions to get to the final answer. And as an example here, one thing that we tried to do was to build, basically build machine learning models of the Mermin free energy functional for finite electronic temperature. And one of the issues is that conventional machine learning potentials are fitted, you can fit them only at one given electron temperature because they only depend on the position of the atoms. So what we did here was finding an expression that predicts the Mermin functional, approximates it based only on ground state information, the ground state energy and the ground state density of states. And then this integral is dirt cheap to compute. So we predict this energy and this density of states, and with this we can estimate the Mermin functional at any temperature very accurately, and basically we can do the equation of state of hydrogen up to 50,000 Kelvin. And yeah, this is just a little detail. This is actually more than what we did for nickel, which was run the heat capacity with ground state potential and add a correction on top of it. If you are at really high temperature, there is a difference between sampling the potential energy at the ground state and adding an electronic correction and sampling according to the Mermin functional. So another thing that we are trying to do is to also start incorporating experimental data. And this is very interesting because of the conceptual difference between what an experiment computes and what a quantum calculation does. We are doing a lot of implementation work. So we are trying to implement all of these techniques in kind of a modular way. So, if you don't care about machine learning, but you want to use the path integral machinery, you can use IPy. If you don't care about machine learning, about path integrals, but you care about machine learning, you can use some of the tools that we're developing for that. If you just want to visualize the outcome of your simulations, you can use Chemiscope, which is just a viewer. And I think that this modular setting is what will make this most useful, not only to us, but to people. And this is, this moment on code is also a very good moment to thank and acknowledge all the members of my group, as well as the funding bodies who support our work. And with this, I think we have 5 minutes for questions, and I'm leaving you for a few references if you want to know more. Thank you.
Thank you very much, Michele, for this amazing talk. You have a few minutes for questions. Who wants to start? I can't see from here, so I will need some legs in the public.
Okay, thank you. Yeah. Okay. Yeah. you listen to me? Yes, thank you very much for your talk. I have a question.
Sorry, could you introduce yourself? Because here you don't know who is speaking.
Okay. Michael Badawi, I'm associate professor in University of Lorraine. I'm working in the group of Dario Roca, theoretical chemistry. And my question is about the modeling of infrared spectra on Raman spectra. I see, so we have a dependence of the level of theory also on those spectra. And in your opinion, how you can get very accurate agreement, a nice agreement with experiments? Because we have always this problem of shifting frequencies. What will be an elegant way to address this issue?
Yeah, I agree. This is why I was kind of being honest when speaking about water, about the fact that we had picked this RFPB 0D3 because we knew that it worked well for water. And those, it's, I think it is a problem. And one way for, I like a lot the work of Francesco Paesani, who is building for water and aqueous systems, these potentials that have low body order interactions trained on high-end quantum chemistry. That's one possibility. It's a lot of work, and I don't know how, there is something nice in the ease of, okay, I run a DFT calculation and I don't worry about it. My personal perspective is that most of the time, the use of simulations is more in understanding qualitative trends more than in getting absolute numbers. So who cares if you have a difference in 100 inverse centimeters on a peak, if you can see how that peak is shifted when you change the solvent, when you change the ion. I think that from a certain perspective, striving for experimental agreement at all costs is perhaps not really needed. So that's why I think it's important to have methods. I mean, all of these approximate methods for quantum dynamics. I mean, you don't really know how good they are. It's very, there is no absolute reference. Experiment is not a good absolute reference because it might be the fault of the potential and not of the quantum dynamics method. So my personal perspective is that it's probably better not to focus too much on the detail, but look at the trends. I don't know if this was an answer or just a politician's answer.
In this case, later.
Yes.
You have questions?
I can ask one if there are no other questions.
Go on, Darius.
I'm Tomasz Buczko. I would like to ask you about the work of where you computed free energy, and you also combined perturbation theory, the calculation with Feynman path formalism.
Yeah.
And yeah, this is what I want to ask. How does it combine? So I understand how it works at so using classical partition function, and how does it work in Feynman path integral formalism?
Yes. So yes, haha. you dig some of details that had swept under the carpet. So okay, so the way it should work is that you have a classical Hamiltonian for integrals, and you do free energy perturbation on that classical Hamiltonian. That would require, one, that you compute, you need to compute the DFT potential on each of the beats. Two, that makes free energy perturbation much harder because the fluctuations in the path integral Hamiltonians are larger than the fluctuations that you get in a classical simulation. So what we did in reality was computing the, we assumed that the correction is classical. I mean, exactly, that the correction is classical, which makes sense because the biggest, so it's clear that essentially the reason why we need this correction is proton disorder, which is something which has a contribution on the electrostatic term. We don't have electrostatics. This is a short-range machine learning model. And that's not something, that's something that you could almost compute based on the ground state structures. Okay, so it's really that bit which is missing. And so basically we compute the machine learning to DFT correction on classical sampling and add it on top of the quantum free energies. We tested that by doing the real thing between two different neural network potentials. We tested that basically it was roughly additive, so that we could do that. But yes, that's you could do free energy perturbation straight on top of Petit integrals. In principle, it's possible, but it becomes much harder because of of how it scales.
Thank you.
Okay, you have time for one last quick question, quick answer from here online from Dario. Dario, go on.
Yeah, no, I had a question about the prediction of the density. First of all, was that like DFT density or some kind of experimental refined density? And it seems sort of a difficult prediction because the density contains a lot of information. So I was wondering if you need a huge amount of data to train your model to predict the density, or
it is the DFT density. It is difficult. It is a difficult prediction. Not so much because of the fact that it contains a lot of information, but because of the fact that you need to predict the density with an incredible accuracy to be able to do something useful with it. So we actually, I mean, to be, again, you guys ask me the difficult questions. So to be honest with you, we have struggled a lot because we were in this situation where we had predictions for the density that looked amazing. But then when we tried to do something with it, we ended up having errors that were larger than if we had made a direct prediction for the end property. Okay, let's say that you predict the electrostatic energy. If it's easier, if you get better accuracy by predicting directly the electrostatic energy, why go through the complication of Wigner-D matrices? Recently, thanks to the persistence of Andrea, we managed to get quite a few examples in which actually this pays off. But it's, in my opinion, it's mostly related to situations in which you have a large contribution from electrostatics, because then predicting the density, which tends to be local and heavily screened, is more efficient than predicting something that has an intrinsic long-range behavior.
Okay. Okay. So yeah, you just replied to my follow-up question. Yeah. So you think that this could be easily extended? So if you train on smaller model, this could be more easily extended to larger system, I guess.
Exactly. Exactly. That's what it looks like is the case.
Yeah.
Okay. So thank you very much, everybody. Thank you, Michele. We should end the talk now, and we'll be back in 10 minutes. Thank you.